So now let's talk about how some other effectors that affect solubility besides just polarity. And let's start with, I'm going to make another solution. And let's say that this is a solution of salt again. So we're going to put in some sodium ions and some chloride ions. And we'll say this is a water-based solution or an aqueous solution. AQ for aqueous. And we'll dump those salt particles in, and as we dump them in, what'll happen is they'll start to dissolve. Now, normally, you wouldn't see a dissolved particle. If you take salt water off of the shelf, you don't see all the salt particles floating around. But I'm gonna draw them in, even though you wouldn't be able to see them, just so we get an idea. So as you dump the particles in, this gets saltier and saltier, and more is dissolved. Okay, up into some threshold. So water can only hold so much sodium chloride. It has a certain solubility. Solubility refers to how much solute can exist in this solution per certain amount of volume. So I'm going to make up a number. Let's suppose that for whatever size beaker I have, whatever volume of water, that the amount I could fit is 100 grams of sodium chloride. And I go and I dump it in, and I'm getting there. I'm getting 90, I'm getting 99, and then I go above that. Let's say I go up to, I exceed that. So the amount that I dump in is actually 110 grams. While floating around in the solution, again, where you couldn't see it, you would see there would be 100 grams dissolved in the solution. And then 10 of those grams afterwards wouldn't fit. They would just crystallize on the bottom or sink to the bottom. They would not be able to stay in the solution. Okay, that would be them down here. So what I've got in this sense is I've reached the maximum capacity plus some extra, and the extra would appear down here on the bottom of the container. So we'll call this situation is referred to as a saturated solution. Saturated, it couldn't possibly get any more solute particles dissolved in there. We're full. And that's different depending on the chemical. For sodium chloride, you can actually fit quite a lot in there before you saturate. But there are other salts that don't dissolve nearly as well as sodium chloride, and they all have solubilities that you could look up in tables and things. All right, that's what they mean by a saturated solution. Now, let's suppose I take this saturated solution, and I'm going to redraw it here, but this time I'm not going to draw all of the stuff that's dissolved, but I will draw the extra. The part that's extra is down at the bottom here. So this is what you would see. You would see clear water. If you tasted it, you would taste all the salt. But then you would see the undissolved salt, the extra at the bottom. And let's say that I put this over a flame and I heat it up. As the water temperature increases, what I would find is some of these particles would go away on the bottom, or they would look like they would go away. They would be dissolving into the mixture. And for a lot of salts out there, for a lot of types of solution, an increase in temperature is an increase in solubility. That at higher temperatures of solvent, we can fit more salt or more solute into the solution. Not all solids behave this way, but a lot of them do. So for most solids, I would say, or most ionic solids anyway, when you heat the solution, you can dissolve more solid in the solution. So they do graphs of things like temperature versus concentration graph would look something like this for a lot of solids. Sometimes you'll get one that goes down, but for the most part, they go up. Okay, that's for solid particles being dissolved into a solution. Now, let's talk about gas particles dissolved into a solution, because solutions are not always solids dissolved, right? You can have gaseous solids. So, for instance, if you took a container of water, let's do another one, and this time you take a hose and you put a hose into the container of water, and through the hose you put some CO2 molecules. And they start to bubble through the water. Some of them are actually going to dissolve in the water. just like the salt dissolved in the water. This would be a CO2 solution. This is like what's in your soda can. Well, we find that for gases, okay, so the similar kind of thing exists where a certain amount could fit, and beyond that amount, you couldn't get more CO2 in there. But for gases, let's say I took this solution now and put a flame underneath it. This is the CO2 solution where it's all dissolved. If I put the flame under it, we actually get less gas that can dissolve in the liquid at higher temperatures. Again, for most gases, there could be probably some exceptions out there. So if we looked at a temperature versus concentration graph for a gas, it would probably decrease with temperature. Okay, we would lose gas. So if you have a soda can and you leave it out and in the hot sun, a lot of that gas will try to bubble out, or it will bubble out faster than if it was cold. With that, let's talk about pressure. So suppose that I had a closed container with a piston at one end. Here's a big, thick, heavy piece of metal at the top end of my container, and let's suppose that I have some water, and then there's a gas up here. Maybe these are like CO2 molecules out here, and some of them are dissolved down here in the water. If I squeeze that piston down, creating more pressure in that container, I will get more CO2 that dissolves into the liquid at the higher pressure. And this is actually how they bottle soda. They want more CO2 in there. It affects the flavor. It affects the fizziness that you taste afterwards. And so at the bottling plant, I think they go up to like 8 or 10 atmospheres. We could look it up. But like 8 or 10 times atmospheric pressure, they squeeze really hard and allows them to put more CO2 into the drink. And then they close the can off at that high pressure. And so every time you open your soda can with that little tab and you hear that, okay, that's because all of the molecules that were dissolved in there at this high pressure are now being, well, first off, the hiss is the pressure being released, and then you get bubbles, right? So if you've ever opened a soda and you see all of a sudden there's bubbles, well, once you release that pressure and you're no longer squeezing all of that soda into there, this would be like if I took the plunger out, then you go back to a low pressure where less gas is available to be dissolved, or there's a lower solubility at the lower pressure. Okay? And that's another factor that affects the solubility. All right. So just to summarize all of the things we had that ionic dissolves to a greater extent or has a greater solubility in polar solvents. We had that like dissolves like. If you want to mix solvents like oil or water or vinegar or all kinds of chemicals, I guess vinegar is more of a solute, but you would say that polar solvents tend to dissolve with other polar solvents and nonpolar molecules tend to dissolve with other nonpolar molecules. If you get something like soap, soap had a little bit of both. We didn't give the word for it earlier, but we usually refer to soap as a surfactant. A surfactant is a molecule that has both a polar and a nonpolar end, so it can kind of dissolve in either medium, and it can help you bring together two different media like oil and water. We talked about how a saturated solution is a solution where you've put so much solute in that there is no more room for more solute, and the excess will just sort of sit at the bottom and not mix. We talked about how temperature increases the solubility for most solids, that temperature decreases the solubility for most gases. And we saw that pressure increases the solubility for gases.